Hello everyone, I welcome you all in the second lecture of 8th week of the course Process Equipment Design, and this is 37th lecture of this course, and here we are going to discuss design of evaporators. If you remember, in the last lecture we have discussed the design of evaporator, and there we have derived the governing equation for triple effect evaporator system and solve those equation using Badger-McCabe method, right. So, in that lecture we have observed that for a single effect we require at least 2 equations. So, we were having 6 equations for triple effect evaporator system. Along with that we have 6 unknowns. So, unique solution were existing. So, unique solution was there, so that we have solved with the method Badger-McCabe, right. So, in this particular lecture we will discuss another method to solve the set of equations which we have developed in the last lecture. So, let us focus on the equation. So, if you recall, for triple effect evaporator system we have this type of equations, right. So, let us discuss these equation. I am not going to details about these equation because that you have already seen in the last lecture. Here we will discuss the non-linearity of the equation. Okay. Now, if you can ask, now someone of you can ask that in all these 6 equation, can we solve these equations simultaneously using, can we solve these equation using linear method, okay, where we can solve set of linear equation using Gaussian elimination method or Gauss-Jordan method, right. But if you see, these equations are basically non-linear in nature. Those methods like Gaussian elimination method and Gauss-Jordan method, these are applicable to solve n number of linear equations, right. But here we have non-linear equation. So, first let us see how the non-linearity will occur in this equation. So, if we focus on the first equation, we have this equation, right. So, if you see in this equation f, Cp, Tf will be known to me, only T1 will be unknown, right. So, this is not a non-linear. Here lambda naught is known to me, V naught is unknown to me, and similarly in this term we have L1 which is unknown, right. So, this equation is purely linear in nature. However, if I focus on second equation, that is this equation, here U1 is known to me, A is unknown to me, T naught is known to me, however T1 is unknown to me, right. So, if I consider this particular term, the equation becomes non-linear in nature, right. So, in this way we can say that one equation is linear. So, in this way we can say one equation is linear and one equation is non-linear for first effect. Let us focus on the second effect. Here, if I consider this equation, L1 is unknown to me and T1 and T2 are unknown to me, right. In the similar line, this A and T1 and T2, all these are unknown to me. Further, if we focus on third effect equation, we can have this equation, and here L2, T2 are unknown to me, and further we can consider A and T2 as unknown terms, right. So, in this way we can find that some of the equation are linear in nature and some of the equations are non-linear in nature. However, if I am having a set of equation and if a single equation in that set is found as non-linear in nature, we consider complete set as a non-linear in nature, right. So, in this way we can say that these equations are basically non-linear in nature. So, we cannot solve these equations simultaneously using Gaussian elimination method or Gauss-Jordan method. So, how I can solve these equation? One point is I can solve that using Badger-McCabe method, which we have already discussed in the last lecture. However, we have another method which considers all these equations simultaneously, and that method is called as Newton-Raphson method, which is very popular method to use set of non-linear equations. Fine. So, nonlinear equations involved in the design of evaporators can be solved with the help of Newton-Raphson method, and formulation of solution of problems in terms of Newton-Raphson method is helpful because it forces one to display the independent equations and independent variables. Okay. So, in this way it consider the solution where independent equation as well as independent variables are clearly shown. Okay. So, let us see how this equation, so let us see how this method is used. So, in this method first of all we give each equation as a function. Okay. So, if I am having 6 equation for triple effect evaporator system, we can consider 6 function as I am having F1 which is equal to the first equation. If you remember, right now when it is at balance, this equation should be equal to 0. So, F1 value should be equal to 0, but right now I am considering that as F1. Okay. And similarly, I am having F2 which is the rate equation, F3, then F4, then F5 and then F6. Okay. So, all these 6 equations we have given a function as F1 to F6, and in Newton-Raphson method we will solve these F functions. Okay. In the similar line, you should aware that what are the known parameters and what are the unknown parameters. So, these parameters we have also discussed in the last lecture for triple effect evaporator system. Okay. So, let us recall that once and then we will start the method Newton-Raphson. So, as far as specifications are concerned, all these parameters are known to me, right? Feed flow rate, like feed flow rate, feed concentration, feed temperature, steam temperature and steam pressure, last effect temperature or pressure, right. And we also know the product concentration or the product flow rate, and all overall heat transfer coefficients we consider equal area, forward feed we have considered, and we have neglected boiling point rise. Okay. So, in this way you can consider that we have 6 parameters which are unknown to me. Okay. And all these 6 parameters we can find while solving these 6 equations simultaneously using Newton-Raphson method. So, let us see how this method works. So, the first step of this method, that is Newton-Raphson method, we convert all equations F1 to F6 from non-linear nature to linear nature. Okay. And how we do this? We do that with the help of Taylor series expansion. Okay. So, I hope you all understand what is this series and how we expand the nonlinear equation with the help of this series, and I am not going into detail of the Taylor series expansion, just I am considering the application of that Taylor series expansion to linearize F1 to F6 functions. Okay. So, let us see how we do this. So, if you consider I am having 6 equations F1 to F6. Okay. So, here we have given a subscript that we consider as J, which varies from 1 to 6, right. So, here I am having Taylor series expansion of one equation, and that we have generally represented as Fj generally, because we want to generalize it, and J we can vary with respect to 1 to 6, fine. So, let us say if function is J, so let us say the function is Fj, okay, we will consider first derivative of this del Fj by del V naught, okay, delta V naught, right. So, basically what I am considering, if you focus on Taylor series expansion, it has the function only, it has first derivative of the function, it has second derivative of the function, and so on, depending upon the variables, right. So, here I am having 6 variable, and for easiness we consider up to first derivative only. Okay. So, if I am having function like Fj, so first derivative of it I have considered as del Fj by del V naught into delta V, fine. Second will be with respect to second unknown, so that equation, so that term will be del Fj by del T1 into delta T1. In this way we can consider Taylor series expansion for 6 different variables, right, considering only first derivative of it, okay, and we can have the function also, okay. So, considering this expansion we can linearize the non-linear equations, okay, and whatever linear equations are there, that term will remain as 0, okay. So, that we will consider further. So in this equation let us discuss other parameters such as delta V naught, and other parameters. So, if I consider delta V naught, that is basically the difference of V naught k plus 1 minus V naught k. It means whatever the value of V naught at, it means whatever the value of V naught is in k plus 1th iteration, that should be deducted with the value of V naught at kth iterations, right. So, in this way we consider all unknowns, okay. So, here we can consider subscripts k and k plus 1 as kth and k plus 1th trial or k plus 1th iteration, right. So, in this way we consider the difference of variable in 2 consecutive iterations, and this difference should remain 0 when I am having perfect solution, fine. So, let us focus on this method further. So, these 6 equations may be stated in complete form by means of following matrix. So, instead of showing these equations individually, we can solve that with the help of matrix, which is easier for us, okay. So, let us make the matrix, and that matrix we consider as the Jacobian matrix, okay. So, here I am having the Jacobian matrix, that is capital J k into variables, that is delta x k, and here I am having the function value, and if you recall the Taylor series expansion, it was added with the derivative term, right. So, here I am having the minus fx value. So, if I consider the Jacobian matrix, that will be in terms of all derivatives like delta f1 by delta v naught, delta f1 by delta t1. So, first row basically consider the first function depending upon all 6 variables, right. So, similarly second row consider second function with respect to all variables. In the similar line I consider all 6 in the similar line I can consider all 6 functions depending upon 6 variables, right. So, let us see what is delta x k. Delta x k is basically the difference in 2 consecutive iteration, and if I am considering k, it means the difference of k plus 1th minus kth iteration. So, in this way I can represent delta x k as x k plus 1 minus x k, and that will be transpose of difference of all variables in 2 consecutive iterations. So, that we can represent as delta V naught to delta A, right, and we consider transpose of that, okay. In the similar line I consider Fk matrix, and that considers all 6 function value f1 to f6, okay. So, if you see this Jacobian matrix, it basically includes all derivative terms, fine. So, here it is basically including all linear terms, not the non-linear terms, okay. So, you can solve. So, once I am having the Jacobian matrix, we represent each term of this matrix with the actual term which are available in 6 functions, right. So, let us see how to do that. So, here you see I am having all 6 functions which we have also discussed previously, and this is the Jacobian matrix. So, if I consider del f1 by del v naught, right. So, del f1 by del v naught will be for this function, and if you see we are considering partial derivative. So, in this term no v naught is there, in this term I am having v naught into In this term I am having V naught into lambda naught. So, value of this term will be lambda naught, right. In this way we can consider other term. Okay. So, if I consider del F1 by del T1, so you see here I am having this value. Okay. So, it should be minus FCP, right. So, in this way we can make the complete Jacobian matrix with the term, and first term should be lambda naught as we have discussed, second term of first row is minus FCP. Okay. In this way you can consider all these terms and you can make the Jacobian matrix like this. Okay. If you differentiate all these terms with the respective variable, you can find this Jacobian matrix, and here I am having some parameters which I have to expand. Okay. So, these parameters are basically B33 you can see and B55. Because of long term I cannot put that over here. So, B33 you can consider as Cp T1 minus T2 minus lambda 1 plus lambda 2. And similarly, B55 I am having Cp T2 minus T3 minus lambda 2 plus lambda 3, right. So, in this way we can consider Jacobian matrix which includes all term without any variable. Okay. So, this is basically you have linearized the nonlinear equation, and these equation are basically set of linear equation. Now, you can solve these equation using any linear method. Okay. So, let us see how to solve that. So, the calculation procedure which you can consider to solve set of nonlinear equation using Newton-Raphson method, you have to take some assumptions, and these assumptions are basically equal temperature difference in each effect. Okay. So, that also we have considered in Badger-McCabe method, considering equal heat transfer in each effect. Okay. So, equal temperature difference, it means delta T1 should be equal to delta T2 should be equal to delta T3. So, that will be slightly different in comparison to whatever you have considered in Badger-McCabe method, right. We have equal vaporization in each effect. So, V1 equal to V2 equal to V3. In this way you can fix L1, L2 and L3. Okay. You have to assume each effect area as equal, and you have to assume value of V naught. Okay. So, considering all these initial value, because first of all you have to initialize the values of unknown parameters and then only you can solve the function value. Okay. So, in this way you can find the solution of Newton-Raphson method. Okay. And so, the solution of triple effect evaporator system. Fine. So, in this course we have considered Badger-McCabe method as well as Newton-Raphson method to solve equation of triple effect evaporator system. Okay. So, from now let us focus on other topic considering multiple effect evaporator system, and that is very important unit of this system which we consider as vapor liquid separator. Okay. So, as you all know that whatever mixture is generated in heat exchanger, okay, because vaporization and boiling takes place in the heat exchanger, and liquid is converted into vapor. Okay. We have to separate these liquid and vapor streams. So, the mixture of vapor and liquid exits the heat exchanger and enters to vapor liquid separator, from where vapor and liquid streams are separated. Vapor exits from the top and liquid settles down, and it can be taken from the bottom of the separator. Okay. So, let us discuss some of the points related to vapor liquid separator. So, the separation of liquid droplets and mist from the gas or vapor streams is analogous to separation of solid particles and liquid. Okay. What is the meaning of that? When the vapor liquid mixture enters into the separator, then what will happen? Because of the circular motion, or we can say the centrifugal motion in the separator, liquid settles down through the wall and vapor leaves up. Okay. So, when the vapor goes up, it takes some liquid droplet with it. Okay. So, vapor with liquid droplet, we can consider separation of this in the similar line as we consider the separation of liquid containing solid particles. Okay. So, in vapor liquid separator, where the carryover of some fine droplets can be tolerated, it is often sufficient to rely on gravity settling in a vertical or horizontal separating vessels. Okay. So, here when I have told you that liquid is moving downward, so that happens with the help of gravity. So, in that case we consider as gravity settling. Along with this, whatever droplets is available with the vapor, it also disengage and settles down with the help of gravity. Fine. So, in this way vapor can be separated, but in this way some of the vapor some of the liquid droplets can be taken by the vapor. Okay. And if we can tolerate, we can separate with the help of gravity settling, otherwise we have to make necessary changes in vapor liquid separator so that liquid droplet will not move with vapor. Okay. So, how we do that? We do that by providing some meshing at the top of the vapor liquid separator, okay, and that we call as knitted mesh demister, and that we call as knitted mesh demister pads, okay, as you can see here. So, here I am having this structure where this assembly is there, where some small droplets are, where some small pores are available. If you see this material, and liquid droplet can be captured by this. So, knitted mesh demister pads are frequently used to improve the performance of separating vessels where droplets are likely to be small and where high separating efficiencies are required. Okay. So, in this case, a small diameter of droplets can also be captured by this pads where high separation occurs between vapor as well as liquid, okay, and vapor whatever is exiting from this pad, it is liquid free or liquid droplet free, right. So, as far as material of these pads are concerned, these are basically made of metal and plastic, and these are available in wide range of the material including metals and plastics. So, you can use these pads to capture the liquid droplet, and you can separate the pure vapor accordingly. Okay. So, now discuss few more points about this, like use of demister pad allows a smaller vessel to be used, okay, because whatever will be the diameter of the vessel, the whole diameter should be covered by this pad. Okay. So, if diameter of the vessel will be smaller, we can place this pad easily. Okay. So, in that case separation efficiency is very high, like it is more than 99%, okay, and it is having low pressure drop also. Further, in some of the cases cyclone separators are used frequently for gas liquid separation. Okay. So, that cyclone separator which works with the centrifugal action, where liquid is spread at the, where liquid is available at the inner wall, and through that wall liquid settles down. Okay. And that somehow happens also in vapor liquid separator, because feed enters into vapor liquid separator tangentially. Okay. So, some of the separation occurred through this section. However, if vapor contains liquid droplet, that can be trapped by demister pads. Okay. So, we can also consider cyclone separator as well as that vapor liquid separator with demister pads. Okay. So, as far as vapor liquid separator is concerned, it can be designed in the same line as we design gas liquid, as we design gas solid cyclones. And here we are having some of the dimensions related to vertical vapor liquid separator, and this is the layout of this. So, if you consider here, we can have liquid outlet and vapor outlet, and diameter of this column is dV. So, if dV is the diameter, we can consider this as a feed inlet, right. So, distance between feed inlet as well as demister pad is dV, okay, and above that we can consider 0.4 meter minimum as the height, and the liquid and the distance between liquid level as well as feed inlet is dV by 2. Okay. So, accordingly we have to design the system considering these guidelines. So, here you see dV is considered as 1 meter minimum, and this should be 0.6 meter minimum. So, if I consider this, then dV should be 1.2 meter. In this way we can consider different dimensions, right. And now we will focus on the horizontal vapor liquid separator. So, layout of a typical horizontal separator is shown here. A horizontal separator would be selected when long liquid hold up time is required. Okay. So, in this case you can consider larger volume and liquid hold up is required much time. Okay. It means it has more residence time, and demister pads are placed at the top of it, as we have discussed in vertical vapor liquid separator. So, vapor exits from the top, but from two different nozzles because of its size, and liquid level, and liquid is also exiting from two different nozzles. Okay. However, inlet is one only. So, liquid settles down, vapor moves up, and then vapor exits through these demister pads. Okay. And here we have the weir to check the liquid level. Okay. And so, in this way we have discussed the horizontal vapor liquid separator, and now we have few more points about this horizontal vapor liquid separator, as the diameter and length and the liquid level must be chosen to give sufficient vapor residence time for the liquid droplets to settle down and for required liquid hold up time to be met. So, in this case we have a specific D by L ratio. Okay. So, what is this ratio is that we will discuss in the next slide. So, and as far as this ratio is concerned, the most economic length to diameter ratio will depend on the operating pressure. Okay. And these operating pressures are, so as far as operating pressure is concerned, if it varies from 0 to 20 bar, we can have L by D as 3, 20 to 35 bar we can have 4 L by D ratio, and similarly if it is more than 35 bar we can consider L by D ratio as 5. So, in this way you can decide height as well as diameter of the horizontal vapor liquid separator. Okay. And vertical vapor liquid separator dimensions we have already discussed, and in this way you can design these separators. Okay. So, in this lecture we have discussed Newton-Raphson method, vapor liquid separator, and in next lecture we will focus on some of the examples related to triple effect evaporator system. Okay. And that is all for now. Thank you.